Good morning. Today we are going to look at estimation. So far we have covered distributions of on modeling severity, and we want to know how can we be able to estimate the parameters corresponding to these distributions. So we look at three methods: the method of movements, the maximum likelihood method, and the methods of percentiles. So we'll begin with the first one, the method of movements. So as we know, the jth movement of a distribution is simply given by averaging the sum of the observations raised to j. So if I want my first moment, which corresponds to the mean, then I'll simply be summing the variables, and each of the variables will be raised to 1 and dividing that by n. So that if I want the second moment, then my j there becomes 2. So my n here is defined as the sample size, xi is my sample observation, and my mj corresponds to the jth moment. So we'll be using that to be able to estimate the parameters of a distribution. So let's look at an example. Okay, before we do that, maybe we can also look at the maximum likelihood so that we can apply the examples to both methods. So under the maximum likelihood estimation, from your test of theory of estimation, I believe you have already done the theory of estimation in statistics. So you begin by determining the likelihood function, for which if your random variable x is a discrete random variable, then you multiply your probability mass function for the entire sample size. If, on the other hand, your random variable is actually continuous, again, you'll still be determining the products of your probability density function. So remember, what this symbol means is that you're multiplying this function over your entire sample's size. The same case here. The only difference is that we're now using a PDF for the continuous random variable, and in this case, you're using a PMF. So once you obtain your likelihood function, respective of the kind of distribution, kind of random variable that is discrete or continuous, then the next step is for you to determine the log likelihood function. So the log likelihood function is simply the logarithm of the previously determined likelihood function. So when you determine the product, when you take the logarithm of a product, that is the same as summing. So you'll be summing the logarithm of the PMF in the discrete case, and you'll be summing the logarithm of the PDF in the continuous case. So we have begun from the likelihood, moved to the log of the likelihood, and after that you can now differentiate the log of the likelihood function with respect to the parameter which you want to actually estimate. And after doing so, taking the derivative with respect to the parameter you're estimating, then equate your function to 0, or equate your derivative to 0, and then solve for the unknown parameter which you're going to be estimating. So let's look at an example. So we use our first example, which is based on the exponential distribution. So suppose that an insurance company uses an exponential distribution to model the cost of repairing insured vehicles involved in accidents, and that the average cost of repairing a random sample of 1,000 vehicles is 2,200. So our task is to utilize the maximum likelihood estimation method to determine the parameter of the exponential random variable. So if we assume that our exponential distribution has the parameter of lambda, we want to determine from this particular information, this is my n, this is my sample size, and this is my mean, which is my x bar, or the first moment, how or what is now my value for lambda. So from we already know from our severity distribution, which we have previously described, that an exponential distribution is actually a continuous distribution, and therefore it means that we will need to determine the corresponding probability density function, that's our PDF, of the exponential distribution. So if you use your tables, you should be able to find that the PDF is given by lambda exponent raised to negative lambda x. So we can now multiply our PDF for the entire sample size, and our sample is of size 1000. So we'll be doing this particular product of the PDF from I equals to 1 to 1000. So our I is going to be affecting the random variable. Our random variable in this case is the x. Our x here representing the claim size, or in this case, the cost of repairing the vehicles. So, so if you multiply a constant lambda 1000 times, that is the same as having lambda raised to 1000. Then in this case, you'll be now again multiplying e raised to negative lambda. The first term will be x1, the next term will still be an exponent base raised to negative lambda, x2, and so on. So you'll find that if you do that 1000 times, then it simplifies to, you can put them all in the same base, which is the exponent base. So you'll have the exponent raised to the negative of lambda, summation of xi's from I equals to 1 all the way to 1000. So if we can go again further and simplify that. So we already know that x bar in itself is given by 1 over 1000 summation of xi's. And in this case, we have the summation of xi's. So if I wanted to make or to express this summation, I can do so in terms of x bar, so that we have our equation simplified as lambda raised to 1000, which corresponds to that. And my exponent now becomes e raised to negative lambda times 1000 of x bar. So this is simply deduced by expressing this summation in terms of the x bar. So we now have our likelihood function, and our next step, based on the maximum likelihood estimation method, is now to determine the log of the likelihood. So the log of the likelihood means simply we take the natural log of this likelihood function. So by taking that, we'll have 1000 ln of lambda, and in this case, we'll have the power, which is negative 1000 lambda x bar times the natural log of the exponent, which simply reduces to 1. And therefore, in that case, we'll simplify our equation to what we have here. So we have defined our likelihood function. We have obtained our log of the likelihood. The next step is to now differentiate the log of the likelihood with respect to the parameter which we are estimating, which in this case is the lambda. So if you differentiate this log of the likelihood with respect to the parameter lambda, then in this case we'll have 1000 divided by lambda, and in this case we'll have 1000 times x bar. So this is your derivative of the log of the likelihood. And once you have this, you can now equate it to 0 so that you solve for the unknown, which is your lambda. And in doing so, you find that your lambda in this case is 1 over your x bar. So to affirm whether it's actually a maximum likelihood, again, from your calculus, the maximum point is determined when, if you take the second derivative of a function, then it should give you a negative gradient. So in this case, if we take the second derivative of this log of the likelihood, so if you differentiate this twice, this function again, so it means this becomes negative 1,000 over lambda squared, and this goes to 0 since it does not have any function of lambda. So since this function is actually less than 0, then we can actually affirm that our lambda estimate here, given by 1 over x bar, is actually the maximum likelihood estimate. So we can go back to our question. So we have already estimated our parameter with respect to a sample moment, in this case the first moment. So in our question we were told that the average cost of repairing a random sample of 1,000 vehicles is actually 2,200. So this is our x bar in itself. So it means that our estimate of lambda, which is what we have here, will be 1 over x bar, which is simply 1 over 2,200. And that is now our final result. So based on that data that had been collected for a sample of 1,000 vehicles, from which it was determined that the average cost was actually 2,200, then it means that from that point onwards, the insurance company can utilize the exponential distribution to model these claims with the assumption that the parameter estimate for that exponential distribution is simply 1 over 2,200. So let's look at another. So if we had now a question, again, maybe from now a gamma distribution, the same approach would be utilized. So you'd need, first of all, to determine the likelihood function dependent on the respective distribution. And once you obtain the likelihood function, the next step is to determine the log of the likelihood, differentiate that log of the likelihood, equate it to 0, and then solve for the unknown. And to affirm whether it is actually the correct value, differentiate the log of the likelihood twice. And if it gives you a negative, if the gradient here is less than 0, then you can confirm that whatever estimate you have arrived at is actually a maximum likelihood estimate. So we can look at another example. So we also have scenarios where if you're looking, for instance, at the normal distribution and you already know that your mean, you have x, which is the claim severity following a normal distribution with parameters mu for your mean and sigma squared for your variances, then it simply means that in both cases you can obtain the parameter estimates by equating them to their sample estimates, so that in that case your mu would be equivalent to your sample mean and your sigma squared will be equivalent to your sample variance. And of course from this you can obtain this from the corresponding moments. I want us now to look at a question which is, yes. So let's look at one on log normal. So suppose that based on analysis of past claims, an insurance company believes that individual claims in a particular category for the coming year will be log normally distributed with a mean size of 5,000 and a standard deviation of 7,500. The company wants to estimate the proportion of claims that will exceed to the 25,000. So if you read that question as it is, it means for us to be able to compute this probability, then we must first of all obtain the parameter estimates for this log normal distribution, because what we have here is 5,000 and 7,500 are actually the sample estimates. So we need to use this to obtain the parameter estimates so that we can actually determine the probability of a claim exceeding our value of 25,000. So we will use this particular approach where we will equate the corresponding parameters that we want to estimate to the respective sample estimates. So in doing so, you can go to your tables where we have the log normal distribution and obtain directly from the tables what is the mean of a log normal distribution, what is the variance of a log normal distribution. So you'll find that from your tables, the mean will be given by this value. So this is your mean, and you can see it is defined with respect to your parameters of interest. Again, your variance is actually the square of this quantity here. So you can confirm this from your from your statistical tables or your actuarial tables. So we can equate the mean of the log normal to the sample mean, and the standard deviation of the log normal to the standard sample standard deviation. And you see, from what we have here, it simply means that we can be able to solve these equations. If you look at this term, it compares to what we have here, and it is simply equivalent to 5,000. So if we replace 5,000 there and make this term the subject, then we are saying that the square root of that function is simply equivalent to 7,000 divided by 5,000, where we have said this term in our standard deviation equates to our mean in this case, which is simply given or equal to the 5,000. So the only unknown in this particular, once we simplify our function or our equation in this manner, becomes the variance or the sigma squared, which we can simply solve by taking the squares on each side and making the sigma the subject, which now equates to 1.179. And once you have this unknown, then you can use the first equation to solve for the other unknown, which is the mu. So if you want to make your mu the subject here, it means you need to take the natural log on both ends of the equation. And once you take the natural log on both ends of the equation, then you can now make your mu the subject. So if you take the ln of this, you'll have mu plus a half of sigma squared being equal to the natural log of 5,000. And in making your mu the subject, then it means you're solving for mu using our equation here, which once you substitute for your sigma squared, it gives you the value of 7.928. So we are looking for, our question was asking, the company wants to estimate the proportion of claims that will actually exceed 25,000. So we have been able to establish the parameters of our log normal distribution. So we now want to use the properties of this log normal distribution to actually estimate the probability of a claim exceeding this amount. So we will use our knowledge of how we approach this question from a normal distribution. So we are seeking to examine the probability that our x is actually greater than 25,000. And if you want to use now the normal approximation, then it means that if my x here is log normally distributed, I can transform it by taking the natural log on each end. And in so doing, it means that I have now created a normal random variable. So this ln of x is now normally distributed with my obtained parameters. So my parameter mu was 7.928 and my sigma squared as 1.179. So we are saying that we know that our x is normally log normally distributed, and we want to use the approximation of these probabilities, or to transform this random variable into a normal random variable. So in doing so, we need to take the ln, and so that we do not change what originally we were looking at, we take the natural log on both sides of the equation, which is what we have done here. And therefore, this now conforms into a normal distribution with the parameters mu and sigma as determined here. So we can now solve for this question the way we do it for a normal distribution. So it means that if I want to determine this probability, then I need to standardize. And how do we standardize? We subtract the mean at the top and divide that by the standard deviation, or the root of sigma squared, or sigma itself. So we have standardized. So we are subtracting the mean on each end and dividing throughout by the standard deviation. And in so doing, this transforms to the standard normal distribution, which is what we are going to be reading from our tables. And this is now the value which we will be evaluating our probability from. So if you go to your tables, let me access the tables. So here we have the standard normal table. So once you evaluate this particular side of the function, you're looking at the value should be 2.025. So we're looking for the probability that our standard normal variable z is greater than 2.025. So if you come to your tables and you look at which side is actually drawn, this is the less than. So it means that you need to read whatever is represented within the tables is looking at less than. But our interest is on greater than. So our interest is on this unshaded area. So if we are evaluating the probability of z being greater than 2.025, so if we assume that our 2.025 is at this point, then we want to seek this unshaded area. So it means that for us to compute the correct probability, we'll have to take the entire area under the curve, then we subtract from it the shaded area, which is what is actually tabulated. So that's why you have 1 minus. So 1 minus the value corresponding to the phi of 2.025. So we'll go to where we have 2.025. So that's our x 2.0. So we only have up to 2 decimal places. So you can read that has 2.03. So we can use this. So it will be 1 minus this entire figure, 0.97882. So and then you can now solve for it. So ensure whatever tables you're using, always examine what the figures within the tables represent, and it will always be guided by the chart that is provided at the start of the table. So we can now clearly see that in this case, 2.1% of the claims exceeded the amount of 25,000. So you can see this is again using the method of movements to now estimate the probability. We have used the method of movements to estimate these parameters, which have now been able to help us solve for this probability. So we can also now, before we go on to the method of percentiles, we have another example here for the method of moments. So claims arising from a particular group of policies are believed to follow a Pareto distribution with parameters alpha and lambda. A random sample of 20 claims gives values such that, so you have your first summation of x being equals to 1508, and summation of x squared being equals to 257 to 12. So by that information itself, you should be guided that we can only use the method of moments, because from this it means you can deduce the first moment by simply taking this divided by the sample. You can deduce the second moment by simply taking this and dividing by the sample. So in this case, you're guided estimate alpha and lambda using the method of moments. So even if this statement was not here, use this part using the method of moments. By the fact that you're given the summation of x and the summation of x squared, it should tell you that in this case, you can only apply the method of moments. So, so we can go ahead. Though it's okay, let me retake that. You can still apply the maximum likelihood estimation method, but by the fact that every time you're given a sample moment, 2 sample moments for that matter, which is often the case when you have 2 parameters, then the easiest method to go for is the method of moments. So unless it is specified, then in that case you may now choose, or you may use the maximum likelihood estimation. And if we were looking at a distribution with 1 parameter, then 1 moment is enough. If we were looking at a distribution 3 parameters, then we would require 3 moments, and we'll see why. So in this case, given that we have the first moment, it means that we can now equate our first moment to the mean of a Pareto distribution, which is defined in terms of the unknown parameters alpha and lambda. So the expectation of x, given x is a Pareto distribution, is given by lambda over alpha minus 1. In the same manner, given that we have the second moment, from this second moment, we can actually be able to express the second moment of the Pareto based on the parameters of alpha and lambda. So if x is a Pareto distribution, what is the expected value of x squared? Then it will be, since this is not tabulated, what is actually given is the variance and the mean. Then we can deduce the expected value of x squared from the two by simply summing them. So if you sum the variance of x and the expected value of x, which is the mean all squared, then you should be able to obtain this value. So we have our first equation, which is the expected value of x, and we have the second equation, which is the expected value of x squared. And now we can now equate the two of them to their corresponding moments. So the expected value of x is equivalent to the first moment, which in our case is the summation of x divided by the sample size, which is 20, which is our equation there. And then for the second equation, we are equating the second moment. So we have expressed our second moment using the Pareto distribution and its corresponding unknown parameters. And now you can equate that to the sample, the second moment for our sample, which again is given by the summation of x squared divided by our sample size. So we have this. So because we have two unknowns, my alpha and my lambda, then you must have at least two equations to be able to solve for them, because that is the only way you'll be able to form two simultaneous equations which can help you solve for the two parameters. So you need now to solve from here, solve these two, so that you can now express one parameter in terms of the other. And in doing so, once you obtain, let's say, your alpha, then you should be able to use either of the equation to obtain your lambda. So you can solve for these two equations in a simultaneous way. So ensure you undertake this or simplify this so that you're able to verify that your alpha is 9.63 and your lambda is 650. So, and what has been done, let me see what has been done. So in this case, you can actually express your lambda in terms of alpha, which means that your lambda will be equivalent to 75.4 times alpha minus 1. And if you square that, sorry, so if you square that, then what will be remain would have 2 times 75.4 squared times alpha minus 1 squared. And this will cancel with one of them, so that what remains is actually what we have here. And once you have this, the entire equation is in terms of the only unknown here being alpha, so you can solve for alpha. So once you solve for alpha and obtain it to be equivalent to this, then you can substitute it in this equation and now solve for your lambda. So ensure you do undertake that to confirm. So you can now look at the other method of percentiles. So you'll find the other or that method which is suitable for some distributions where it may not be possible to actually use the earlier methods. Then the method of percentile comes in. So we are looking at a Weibull distribution. So suppose we have a Weibull distribution, again determining or estimating our claim severity. And we now want to estimate the unknown parameters of C and gamma in our Weibull distribution using the method of percentiles, where the first sample quartile is 401 and the third sample quartile is 2836.75. So remember the aspect of quartiles. A quartile means we have divided our data or our distribution into 4 parts. So if we speak of the first quartile, we're looking at the first quarter. If we speak of the third sample quartile, we're looking at the quarters of the distribution or the quarters of the data. So if we were to solve for C and gamma using the method of percentiles, then it means we will be utilizing the cumulative distribution function, where we'll be saying if we were to integrate our PDF from its list value, assuming the domain of X in a Weibull distribution starts from 0. So if we were to integrate that function from 0 all the way to my first quartile, then that probability should be equivalent to 0.5. That simply means if we are evaluating the probability that X is less than or equal to my first quartile, then that probability should be 0.25. So essentially, when we speak of the probability of a function, the probability of a random variable being less than or equals to a specific value, we are simply evaluating the CDF at that point. So it means that in our case where the first quartile is actually 401. So our first quartile, which is 401, is simply equivalent to the CDF, or the cumulative distribution function, at 401. And this CDF simply represents the probability that my random variable X, which in this case represents claim severity, average cost of claims, then that probability we are evaluating it as being less than or equals to the first quartile, and that should be equivalent to my 0.25. So that's why we are substituting where we have X, we simply substitute with the corresponding quartile. So if we say that probability, this is the probability that my X is less than the first moment, and we are already told that the first moment is 401, it means we are evaluating that CDF at 401 as my X value. In the same manner, we are told that the third sample quartile is actually 2,836. So again, we are looking at the probability that my random variable X is less than the third quartile. And what is my third quartile? It's simply the 2,836.75. So we'll be replacing that in our CDF. And ideally, that probability should be equivalent to 0.75. So this comes from the 3/4 or the third quartile, meaning that we are dividing our distribution into quarters, and the third quartile simply represents 3 out of 4 parts. The first quartile represents 1 out of 4 parts. So once you express your equation like so, you can see again we have 2 unknowns, and therefore it is paramount, or it's important for us to have 2 equations so that we can be able to solve the equation simultaneously. If you only had one of them, then it's not possible to actually solve for C or the gamma. So it's important to have 2. If you have 2 unknown parameters, then the least equations you should have are actually 2. So from here, you can now take this, you can take the ln on both sides. So you know the ln of 1 is 0, so we are left with, and the ln of the exponent is simply whatever is in the power. So you have that being equivalent to this should be the natural log. I think there's a mistake from this step to that step. So you're simply taking or simplifying the 2 equations so that you're able to solve for C and the gamma. So if you take the natural log of 1, that should go to 0, and you'll be left with negative exponent raised to this power. So if you take the ln of an exponent, you'll be left with whatever is in the power, which is what we have here. Okay, I know what has happened. Before you take the ln, you can take this one to that other side, or vice versa. So if you do that, you'll have negative exponent, all that being equals to a negative 0.75. So to get rid of the negative, you can divide again through what by negative 1. So if you do that, you'll be left with the exponent of that being equal to positive 0.75. So from there, you can take the natural log. So if you take the natural log of the exponent, it remains as the power, which is what you have there. And on this other end, it will be the ln of 0.75. Then the same thing here. So we can take this one to this other end. So we'll have the negative of that exponent being equals to negative 0.25. Divide the root by the negative, so you'll have a positive exponent and you'll have a positive 0.25. Again, take the ln on both sides. So you have your function here. So there's a negative c, there's a negative c. So if you added these two equations, now if you actually subtracted them, does that, yeah. So if you divide both of them by c, we now want to simplify this further. So if you divide, so if you can divide both of them, yeah, because this is actually a product and not, so you'll get rid of the c, and then you can now solve for gamma. So once you solve for gamma and obtain this as your value, then you can now substitute it in one of them so that you now solve for c. So the most important thing is how to expressing these particular percentiles, so that once you form the equations, then the rest is simply simplifying. So we can look at another example. So claims arising from a particular group of policies are believed to follow a Pareto with parameters alpha and lambda. A random sample of 20 claims has a lower quartile. So lower corresponds to the first quartile, lower quartile of 11, and an upper quartile of 85. Estimates the values of alpha and lambda using the method of percentiles. So we use so similarly to what we've done in the earlier question, we use the CDF because in evaluating these quartiles, we are looking for the probability that our random variable x is less than or equals to a specific value. And by that, it simply means we are substituting our CDF at a particular point. So in doing so, if you were to evaluate the lower quartile, which corresponds to the first quartile, it simply means where we have our x value, we are evaluating it at Q1. So where you have x there, you replace that by Q1. That quartile, in the same manner, you replace that by Q3. So we go ahead and so if you are evaluating this first quartile, ideally what it means is that that probability that your random variable x is less than the first quartile Q1 should be equal to a quarter of the distribution. And in the same way, if we are evaluating the third quartile, we are simply saying that probability that of your random variable x being less than Q3 should be 3/4 of your distribution. So that's why you have the 0.75. So we want to estimate my alpha, my lambda, my alpha, my lambda, and we already given the values for the lower quartile as 11. So my Q1 is already given as 11, and my upper quartile, which is the third quartile, is already given as 85. So we can simplify this further so that we express the unknown, or we write it in terms of Q1, which is already known, and they do the same for the second equation. Express this equation in terms of Q2, which is what we have here. So what has happened, this one has gone to the other side, and you have now been able to make your Q1 the subject in both equations. So once you do that, substitute for Q1 and Q2. And once you do that, then from here, you can now eliminate your lambda here by dividing these two equations, so that you have this as now your new equation. And you can see this equation only has an unknown as negative 1 over lambda, 1 over alpha. So when it only has one unknown, it means you solve for the unknown. So in solving this, you should obtain your alpha as 1.284, and your lambda can now be obtained once you substitute this value in either of the two equations. So those are the three methods which we shall be considering: the method of moments, the method of percentiles, and the maximum likelihood estimation methods. So once you solve for your parameters using those methods, then the next thing for you to do is to carry out a goodness of fit test. So by that we simply mean you will have observed a certain experience over time after assuming your distribution. So today, for instance, you'll settle for an exponential distribution to model the average cost of claims for your motor insurance policy. So you'll have that to do the estimates, but over time you'll find you'll have a certain observations. So you need to measure whether your distribution is actually, how is your distribution performing with what is actually being experienced. So we shall apply the chi-square test for the goodness of fit, where we seek to determine how far off are my observed values far from what I expected from my distribution. So this is the chi-square statistics which we shall be applying, and ideally we are saying that we will have assumed a certain distribution which will now give us the expected number of claims which we can actually predict using certain probabilities. But now over the years we'll observe actual observations which will deviate from what we predicted. So to evaluate whether we should continue to use a certain distribution, we will evaluate using the chi-square. So we'll use a question to answer this or to demonstrate this test. So we're still using, suppose that an insurance company uses an exponential distribution to model the cost of repairing insured vehicles that are involved in accidents, and that the average cost of repairing a random sample of 1,000 vehicles is actually 2,200. And the breakdown is as shown in this table. So this is now what has been the experience. What has been estimated historically is that they follow an exponential distribution, and we already established the parameter lambda based on this data, which was 1 over x bar. So now we want to see, has been our prediction based on the exponential been what has actually observed in this particular class of insured vehicles. So we'll use this data. So what does this data tells us? It tells us that the repair cost is between this much, and this is the expected number. So a repair cost of between 1,000 and 2,000, what has been observed is actually 3,000. So In this case, we're simply evaluating a hypothesis, and our hypothesis in the null states that the repair costs are actually exponentially distributed, against a null hypothesis that the repair costs are not exponentially distributed. So we'll use the chi-square. So we will need to determine what has been the expected number. So this is our observed data, and from our statistic we have the observed, which is already what is tabulated. We now need to compute what is the expected based on our distribution. So we'll do it for each of the bands of the repair costs. So we will need, it's like we are constructing another column here, the expected number. So what was the expected number based on our model of repair costs costing 0 to 1,000? So we'll feed it there. What were the expected number of repair costs for 1,000 to 2,000 and so on. So we'll demonstrate it for one of the bands. So what has been chosen is 2,000 to 3,000. So we are looking, or we are seeking to determine what is the expected number of claims within that will realize a cost of between 2,000 and 3,000. So what this exponential distribution will do for us, it will simply estimate the probability that a claim lies in this particular interval. And once you get that probability, then you can multiply it with the sample size to get the expected number of claims that will actually be within this particular band. So this is our exponential PDF. So we're going to be integrating it for the corresponding limits of the repair cost, so that we are able to tell what's the probability that an individual repair cost will actually fall in that category. So, and remember, our lambda estimate based on the maximum likelihood example we did earlier was arrived at as 1 over 2200. So if this was not given, then you did first of all to compute your lambda, obtain it as this, and now apply it in this particular test of hypothesis, or this goodness of fit question. So if you integrate this, this becomes your solution, substitute for the limits, and then you can substitute for your lambda. So this becomes the probability that an individual repair cost will actually fall in this band. But now we were looking at, so our random sample was actually 1,000 vehicle. So if we were evaluating 1,000 vehicles, how many would we expect to fall in the category of accruing a repair cost of 2,000 to 3,000? It simply means you take the probability of an individual repair cost appearing in that interval and multiply it with the sample. So this becomes 147.2. So this will now correspond to the expected number for this particular category. So it will fall here. So if you do the same for all the bands, this will be the corresponding expected number for 0 to 1,000. This will be from 1,000 to 2,000, 2,000 to 3,000, 3,000 to 4, and so on to the very last category. So once you now have your data on observed from the table, the expected is what you have computed in this manner for all the categories. Now you can solve for your chi-square test statistics. So you'll be taking the observed in each category, subtracting from it the expected, squaring that, and then dividing it by the expected. So you do it for the first, you do it for the second, up to the last category, then you sum that quantity. So this now becomes our chi-square, test statistic. So when you're doing evaluation of hypothesis, you compute your chi-square, you compute your test statistic and compare it against the tabulated figures. So for us to be able to tabulate or to determine the value which we are going to read, we must assume a certain confidence interval, as well as, for the sake of the chi-square, the number of degrees of freedom. So usually in a chi-square test statistic, we take our degrees of freedom to be simply n minus 1. However, if we end up estimating a parameter, then we must reduce the degrees of freedom by the number of parameters we actually estimate. So in this case, my number of categories or the number of intervals will correspond to my sample size. So we will not use the sample size of 1,000, but rather the number of intervals which we have used in computing these test statistics. So we'll use these categories here. So we used 1, 2, 3, 4, 5, and 6 categories. So my n is 6. And as a rule of thumb, it is n minus 1, so 6 minus 1. Have we estimated any parameter? Yes, we have. We have estimated our parameter of lambda, and this is therefore one parameter. So we reduce that again by a further one parameter. So it means if we are looking at an instance where our repair costs were modeled using a Pareto distribution with parameters alpha and lambda, then in that case we'll have had to reduce our degrees of freedom by 2 instead of this particular one. So a rule of thumb in determining the degrees of freedom, it's n minus 1, and then minus any other number of parameters which have been estimated. So we have determined our degrees of freedom. So you can choose if you're not given. So our question was not specifying, our question was not specifying the confidence interval to assume or the level of significance. So you can assume anything from 95 and above. So in this case, what is utilized is actually 99.95. So again, we can go to our tables, the chi-square tables. So here it is. This is the chi-square. So we have established that our degrees of freedom are 4, and now we want 99.95% confidence interval. So we go to where we have that. So this V here defines the degrees of freedom. So we can go, is this the correct table? This is the probability table. Okay, yeah. So here it is. So we are looking at V equals to 4. And the probability which we are evaluating is 0.995, page 169. Okay, so you can see the difference. This is the one that is actually giving us the probability P, which we are seeking, which is different from the original, this particular graph. What this graph is showing is actually the CDF. of the chi-square. So our interest is on the table representing the probability, which is what we have here. So again, the V represents the degrees of freedom. So our interest is on 4 degrees of freedom. And we're looking at 99 points. Why? 99.95. This is our probability. Just a moment. The up. Yeah, sorry for that. I needed to verify. So this is our shaded area. So it means whatever is actually within these tables represents this shaded area. So if we want, so if you want to evaluate it at the upper interval, or simply our confidence level to be 99.95, it means we should correspond to an area where, so this area is what should be represented by then 99.95. So as it is, if we go directly to what we have here, the 0.063 whatever, this is representing this small area. So if you want this area, it should be represented by me choosing this probability here to be 100 minus the 99.95. So we should read the corresponding p-value as 100 minus that is 0.05%. So we should go to where we have 0.5%, which is what we have here. Is that the correct? Yeah. Yeah, 0.5% plus 99.5%. So that this is now the area which is unshaded, which is what we are examining. So in this table, you can see the difference if you compare this to what we had for the normal. In this case, if you now want this less than side, which is our interest, then you will have to subtract or read the tables, read these particular probabilities in the reverse manner. So you'll have to take 100, for instance, minus whatever you're looking for, so that this is our value corresponding to that 99.5%. So if you were looking at, for instance, if you go back, if you were looking at 90%, so instead of, still for the same degrees of freedom, instead of reading this as our value, you'd go to where you have 10% and read this as your correct value. In a similar manner, if you were looking at 95% confidence interval, then this becomes your value. So if you look at, so we have our test statistic is 331.89. Our tabulated value for this degrees of freedom is 14.86. So our test statistic is less than our tabulated value. So in that case, we actually reject. So every time your test statistic is less than what is tabulated, you reject your null hypothesis. So we're saying, so in this case, because this test statistic is less than uh, 14.86, then we reject the null hypothesis. And by us rejecting the null hypothesis, remember what he had stated, we are simply saying that by rejecting the null, we are simply saying that the repair costs do not actually conform to the exponential distribution, or they do not follow the exponential distribution. So ensure you complete this particular example by evaluating these quantities or these expected values so that you can be able to compute this exact test statistic. So again, I'll leave a question for you to attempt, simply borrowed from what we've already learned here. And that shall be it for this lecture.